Hi everybody, I hope this video finds you well. In this video, we're going to be finishing up section 4.2 from your textbook, which is the introduction to vector spaces. In this video, we're going to do a couple things. First, as you can see on this sort of page here, we're going to go ahead and discuss some common vector spaces. These are just things that we're going to just briefly talk about. We're not going to go through and prove all 10 properties, and we're just going to sort of assume that they would hold through sort of our common knowledge of these different constructs. So we'll talk about these sort of common vector spaces. Then we'll talk about some further properties of vector spaces. In other words, some properties that can be derived from those 10 basic properties that you have to prove to show something as a vector space. And then we'll wrap this whole thing up with one more example of actually confirming something is a vector space, but we'll take a look at something that actually has some non-standard operations. But to begin with, let's talk about these common vector spaces. So here are sort of 5 common vector spaces that we'll encounter in our class, and after we've sort of had this discussion, we're just going to have the assumption that if we're ever working in one of these, we don't need to go through and reprove that they are vector spaces. We'll just take it as common knowledge that these are all vector spaces. So the first one here, right, is the one that you guys probably are most familiar with. It's Rn. Rn is the set of n tuples of real values when you have standard vector addition and standard scalar multiplication, and that is a real vector space, meaning that is a vector space if you use your scalars to be the real numbers. Very similar to Rn is Cn, which is the set of n tuples where each value, instead of being a real value, is actually a complex value. And you still use standard vector addition and standard scalar multiplication. Then, interestingly enough, because you are using complex values, you can have your scalars be the real numbers or the complex numbers. So Cn can be viewed as both a real or complex vector space. Rn is not a complex vector space because if you imagine with Rn, it would not be closed under scalar multiplication if you used complex scalars, right? Because if you multiply a real value by a complex value, you're going to get a complex value, which would take you out of Rn. But Cn, on the other hand, is both a real and complex vector space. So you can use real scalars or you could use complex scalars. All right. These ones are sort of the ones that you encounter in geometry and multivariate calculus. Now we're going to talk about the ones that are more unique to our class, the objects that we've been studying like matrices, and the objects we're going to be studying later on, which are going to be sort of functional sets for solutions of differential equations. So first one here is this one called m by n of R, a little bit of a weird name, but what that is it's the set of matrices that are size m by n with real elements. And if you use standard matrix addition, so element by element addition, and standard scalar multiplication for matrices, then that is a real vector space. A small note here, if you ever see this written, mn of R, then this is the vector space of n by n square matrices. So if you ever see it written with just a single subscript rather than 2 subscripts here, then you're assuming that you're talking about square matrices that are size n by n. So this actually is a vector space if you use the standard matrix addition and scalar multiplication. That should make sense. We know that matrix addition is commutative and associative, and we know that there's a distributive property. So all those 10 properties would hold, and we pretty much proved all of them when we did our section on matrix algebra. All right. Next one is Pn of R. So this is the set of polynomials of degree n or less with real valued coefficients, standard polynomial addition, and standard scalar multiplication. And this is a real vector space. We actually did this example right in the second video where we went through and showed all 10 properties. We showed directly we proved directly, let's say that. We proved directly that P3 of R is a VS, right? So we did it in the specific case where n is 3, where we talked about polynomials of degree 3 or less, but in general, all of our work that we did in that proof would have held for any degree as long as it's degree n or less. So we now have this general class of vector spaces, the polynomial spaces. Finally, sort of similar to that is this one called Cn of R, which is the set of real valued functions that have at least n derivatives with standard functional addition and standard scalar multiplication is also a real vector space. Now, that means like, C2 of R would be all the real valued functions out there that have at least two derivatives, right? Meaning two well-defined derivatives there. A couple notes here. If you see this notation, C0 of R is the set of all continuous functions, right? So C0 of R is the set of all continuous functions, meaning they might have derivatives, but they at least have to be continuous. And if you ever see this, C infinity R is the set of all infinitely differentiable functions. So this would be all things that have an infinite amount of derivatives, where you can keep taking derivatives and not run into any issues. Now, if you think about it, this Pn of R is actually lives inside of these guys here, because polynomials are always infinitely differentiable. So this guy actually lives in here. It also lives in here. So the polynomial space is sort of a special example of these spaces of differentiable and continuous functions. Now, these guys in here are going to be pretty important to us. We've been studying matrices already, so it's nice to know that they are a vector space. And these guys are going to become very important when we sort of return and use linear algebra, which is what we've been studying now, to help us with differential equations. So we'll be working in this sort of space quite a bit. All right, so now that we've had this discussion, you guys are sort of allowed to assume that if you are working in any of these vector spaces, Rn, Cn, M by n of R, Pn of R, and Cn of R, as long as you're using the standard operations, standard addition, and standard scalar multiplication, you now know that those are all vector spaces. All right. Next thing we'd like to do is talk about a few further properties of vector spaces. Now, these things are not going to be properties that you have to show are true every time you're proving something is a vector space. Instead, they're things that if something is a vector space, you get to know based on those 10 properties. So these are sort of results or corollaries of the 10 properties of vector spaces. So let's talk about those. So these further properties of vector spaces. So these hold for any vector space. If you have a vector space V over a field F, the following are true. First, when we use that language of saying that there is a zero vector, we really can say a zero vector, because the zero vector must be unique. So there is only one zero vector. Two, right? This says that the scalar 0 times any vector v must result in the zero vector. So in other words, when you multiply by the scalar 0, you end up with the zero vector. Property 3 says that if you multiply any scalar with the zero vector, it remains the zero vector. Notice these are both things that you would expect about a zero vector, right? But we're just saying that these are indeed true. 4 is sort of similar to 1. It says that the additive inverse that we know must be true in any vector space. We know that one of the properties of a vector space, one of the axioms of a vector space, is that it must have additive inverses. Well, this is saying that those additive inverses must be unique. 5 is very important. It tells us that when we use that notation of negative v, that really is equivalent to negative 1 as a scalar times v. So in other words, that negative v isn't just notation. It really is equivalent to negative 1 times the vector v. Finally, this last guy is sometimes called like a zero divisor property or something like that, which this says if you have a scalar from your field and a vector from your vector space, and you have your scalar times your vector is the zero vector, then either the scalar is 0 or the vector is 0. In other words, you can't take two non-zero things, multiply them together, and get 0. One of them must be 0 if their product is 0. So All 6 of these properties come from the 10 basic properties of vector spaces. Your textbook goes through and proves a few of them and then leaves other ones as exercises. I do think since these proofs are a little weird, it is worth talking about them. So we're going to go through and quickly prove all 6 of these further properties. Once we've done this, of course, now they will be things that you guys can use. You don't have to reprove them. I just want you guys to at least see once how you would prove each of these things. So let's go ahead and talk about those. So first one that we want to talk about is we want to show 0 vector is unique. Okay, so to do this, let's assume you have 0, 1 and 0, 2, both 0 vectors. Okay, so we're going to assume that you have 2 0 vectors. So if we're going to show that the 0 vector is unique, then what that equates to is we need to show that this guy, 0, 1, is actually the same as 0, 2. In other words, if you have multiple 0 vectors, they really are just the same, which would mean that the 0 vector is unique. So we need to show this. Okay, so let's go ahead and do a proof of that. So since 0, 1 is a 0 vector, then what does that mean? That means v plus 0, 1 equals v for all v in our vector space. All right, that's the definition of being a 0 vector, is that when you take a vector and add it to the 0 vector, you get that same vector back. Since 0, 2 is a 0 vector, then v plus 0, 2 equals v for all v in v. That's the same definition, just saying that 0, 2 is supposed to be a 0 vector. Okay, so what does this tell us? Well, then this tells us that 0, 1 plus 0, 2. Well, what can we say about that? Well, if we're taking 0, 1 and adding it to 0, 2, and do keep in mind all of these, my sort of poor notation, there should be the vector addition symbol. There we go, sorry about that. If we're doing that, well, we're saying if you take 0, 1 and you add it to 0, 2, according to this, right, anything plus 0, 2 should give you that same thing back. So this should be equivalent to 0, 1. And that's since 0, 2 is a 0 vector. Okay, so that's nice to know then. But, right, plus is commutative, right? We know that. So 0, 1 plus 0, 2 is the same as 0, 2 plus 0, 1. And if you think about this, well, any vector plus 0, 1, according to this here, must result in that original vector. So this is equal to 0, 2. So what do we have there? Well, we have 0, 1 plus 0, 2 has to be 0, 1. We have 0, 1 plus 0, 2 also has to be 0, 2. So 0, 1 plus must be equal to 0, 2. Check. And that's exactly what we wanted to show. So we've shown that the 0 vector must be unique. So when we say the 0 vector, we really mean the 0 vector. There is only one 0 vector out there. Okay, so that proved the first one. Let's take a look at the next. So for 2, right, we want to show, we need to show that 0 scalar multiplied with v is equal to the 0 vector for all vectors v in v. So that's what we need to show. That's the statement of that. So let's go ahead and take a look at how we do that. So let's see what we can say about this. Notice we're going to try to sort of work from this side over to here because we need to show that equality. So what I'm going to do here is a little bit dumb to start with, but I'm going to consider this as 0 plus 0 and then scalar multiply that with v. Now notice that the plus here is just a normal plus because this is the 0 scalar plus the 0 scalar there. All right, now we know that scalar addition distributes over scalar multiplication. So we can write this as 0 scalar multiplied with v, vector addition 0 scalar multiplied with v. And if we want, we can put sort of parentheses showing us that those are different vectors there. Okay, so what do we have then? So this tells us that 0, if we just look at the two ends here, this And this must equal this guy. Okay, now this is a little messy, so let's just do a little trick here. Let's let W equal this thing here to clean this up a little bit. So this would become W equals W plus W. Okay, now remember this thing here is a vector. This W is a vector. So negative W exists, right? It must, right? We know that every vector in a vector space always has an additive inverse. So let's add that to both sides. So plus negative W is W plus W plus negative W. And we know that when you have something plus its additive inverse, you get the zero vector. So this would be 0 equals W plus 0 vector. And then we know that anything plus the 0 vector must be that same thing. So we get 0 equals W. Well, what was W here? Well, W we defined as that guy right there. So we get 0 equals 0 scalar multiplied with V. Well, if we look at that, it's reversed, but that's exactly what we wanted to show. So we prove that if you take the scalar 0 and scalar multiply it with any vector, you get the 0 vector. Okay, let's go ahead and take a look at 3. Oh, we'll need a couple more pages here. All right, so let's go ahead for 3. For 3, we need to show that k times the 0 vector equals the 0 vector for all k in our field. All right, so let's think about how we would go through and do this. Well, what can we say about this guy here? Well, this guy, I mean, again, some of these proofs are not necessarily immediately obvious, but let's see if we can sort of play around with it. We're going to try something sort of similar to how we did the previous one here. So let's go ahead and actually talk about this. So let's do this guy. So let's introduce another vector here. Let's let V be an element of our vector space. So what can we say about this here? Okay, so we're going to consider this k times 0 to be equal to this guy here. Okay, well, we can say, well, actually, let's write it the other way, just to make it a little bit clearer. Okay, let's take this guy, kv plus k0. Okay, what can we say about this here? Well, if we take a look at what this is, then we can say that that is by sort of undoing this distributing, which we know is possible because we have a distributive property. We can think about that as k, and then we should be using our scalar multiply. My apologies here. K with v plus k scalar multiplied with 0. Okay, so what are we going to do with this? Well, we're going to sort of imagine factoring this k out. So let's take this as k scalar multiplied parentheses v plus the 0 vector. Okay, so what do we get there then? Well, we know that anything plus the 0 vector just has to result in the same thing. So this would become k scalar multiplied with the vector v. So let's look at the two ends again, sort of what we got here. So we know that k scalar multiplied with v plus k scalar multiplied with the 0 vector has to be k scalar multiplied with v. Okay. Now, if you think about this, this is saying that this vector plus this gives you back the same thing. So this plus this gives you this. Now, this was true for any v in v. So that this here then, that's acting as the 0 vector, because the definition of the 0 vector is something plus the 0 vector equals that same something. So equals the 0 vector. Since the 0 vector is unique, right? We know that the first thing we proved is that there's only one 0 vector out there. This guy is acting as the 0 vector, so this must be the 0 vector. And if you think about that, that's exactly what we wanted to show. right? We wanted to show that k times the 0 vector is the 0 vector. Okay, perfect. So let's go ahead and look at the next one, 4. So for 4, we wanted to show additive inverses are unique. Okay, so let's let V be an element of our vector space, and suppose that U and W are both additive inverses. What we need to show then is we need to show that U equals W. So what does it mean to be additive inverses? Well, so this will be our actual proof here. So since U, W are additive inverses of V, what that tells us is that V plus U is equal to the 0 vector, and V plus W equals the 0 vector. Okay, now since both of these equal the 0 vector, then right, we can say that V plus U has to be the same as V plus W. Okay, but now let's be a little clever here. Let's add one of these guys, one of these additive inverses on both sides. So that tells us V plus U plus W equals V plus W plus W. Okay, so I'm just adding this W vector on both sides. Now, over here, right, what I'm going to sort of note is that on this guy, we can sort of change. We know that vector addition is commutative, so let's change the order of this. So let's make this V plus W plus U equals V plus W plus W. But now let's use the properties that these things are additive inverses. We know that V plus W is the 0 vector. So this is the 0 vector and this is the 0 vector. So that would be 0 plus U equals 0 plus W. Right? Just by recognizing that any V plus W is the 0 vector. Well, what happens when you add the 0 vector to a vector? It doesn't change anything. So if we go on to the next page here, so we had 0 plus U equals 0 plus W. So that tells us that U equals W. And that's exactly what we wanted to show, namely that the additive inverse here, right? We needed to show that those two additive inverses were the same. So when we talk about an additive inverse, we can say the additive inverse, and we're all safe in saying that. Okay, let's go ahead and talk about property 5, right? So we need to show that negative V equals -1 scalar multiplied with V. Well, to show this, what we're going to do is, let's go ahead and take a look at V plus -1 scalar multiplied with V. So now we're basically needing to show that the additive inverse here is really -1 scalar multiplied with the vector. So let's add the vector to this thing we're claiming is its additive inverse. So if we do that, what can we say here? Well, we can think about that as 1 scalar multiplied with V plus -1 scalar multiplied with V. We know that that's allowed because one of the properties we have of vector spaces is the unit property, that any vector can be thought about as 1 times that vector. Now we're going to use the distributive property to view that as 1 plus -1 scalar multiplied with V. Right? This is saying that scalar addition distributes over scalar multiplication. And notice that this addition here would be normal addition, right? Because this would be addition of two scalars. And we know that that would become 0. And we just showed that if you ever take 0 and you multiply it with a vector, well, you know you get the 0 vector. So what does this show us? Well, this shows us that V plus this thing here equals the 0 vector. So -1 V is the additive inverse of V since additive inverses are unique. In other words, the sort of logic of this that you guys have to sort of catch here is that we showed that -1 scalar multiplied with v is an additive inverse, but since we showed in since we showed in part 4 that additive inverses are unique, well, this confirms that this guy is an additive inverse, and since additive inverses are unique, he is the only additive inverse. So negative v really is the same as -1 scalar multiplied with v. All right, last part here. Let's go ahead and look at 6, right? We need to, we're going to assume that k scalar multiplied with v is equal to the 0 vector. We need to show k equals 0 or v equals 0. Okay, so let's assume k not equal to 0. Then we need to show v equals 0. Okay, so we have k, v equals the 0 vector here. So we're assuming that k is not equal to 0. We need to show that v equals 0. Well, if k is not equal to 0, then we can multiply both sides by 1 over k. So 1 over k times k, scalar multiplied with v. This right here would be normal multiplication, not scalar multiplication, because it's both scalars. And 1 over k, scalar multiplied with 0. Well, on this side here, 1 over k times k would be 1, scalar multiplied with v. And of course, any scalar multiplied with the 0 vector, is the 0 vector. And as we know, we have that unit property. So 1 scalar multiplied with v, that has to be v, and that is equal to 0. All right, so we showed that v must be the 0 vector. Okay, you might say, okay, well, we assume that k is not equal to 0. What happens if k is equal to 0? Well, then we're done, because we needed to show that k equals 0 or v equals 0. So if we assume k equals 0, we're done, because that's one of the things that we needed to show. So in other words, this is sort of a weird proof, because half of the proof, when you assume k is equal to 0, is basically trivial, right? If k equals 0, then k equals 0. If k isn't equal to 0, then we showed v must be 0. So in other words, one of the two must always be 0. So now we've proven these 6 additional properties. Now, before we get to our final example here, I do want to just call your guys' attention to, not only just these proofs, but what these things really mean. So let's go back and look at these properties we just showed. The really key things you should sort of keep in mind here is that these properties can make it very easy on you when you have non-standard operations. When you guys have standard operations, you can sort of assume that the 0 vector is going to be a vector of zeros. When you have standard operations, you can sort of assume that additive inverses are just going to look like the negative of the normal vector. But when you have non-standard operations, things can be a little weird. So how do you actually figure out what is going to be your 0 vector or what is going to be your additive inverse? Well, these properties tell you how to do it. If you need to figure out your 0 vector, imagine doing scalar multiplication by 0. That'll give you your 0 vector. Need to figure out what your additive inverse is? Well, you can actually do scalar multiplication of -1 in a vector, and that must be the additive inverse. So if you're ever unsure what you should use for the 0 vector or what you should use for the additive inverse, these properties, specifically property 2 and property 5, really tell you how to find the 0 vector and how to find the additive